to talk to us today about demons do not die. Okay, I will leave this for him to explain. Okay, but it's going to be a very, very interesting talk. Let me just introduce you to Dr. Murthy. He is from the School of Physics, not Department of Physics, School of Physics, University of Hyderabad in India. Professor Murthy is also the coordinator of the academic affairs of the Center for Modeling, Simulation, and Design, MSc from that institution. Okay, he has many research interests. Okay, he's expert in many research areas. But very briefly, his research interests include Monte Carlo modeling in statistical physics, also Monte Carlo modeling in radiation transport, random walks, and many others. Professor Murthy has about 200 publications in reviewed, peer-reviewed journals and many other things. He has done his postdoctoral research in Indira Gandhi Center of Atomic Research in Theoretical Studies sections of the materials. So we have no more views. So let's welcome back there.
Thank you very much for a very elaborate introduction. And I only wish that the prediction that you made, the talk will be interesting, come true. And let me say thanks for inviting me to this place. And how much time we have?
We are not in this. We are not in this.
I'm going to talk about demons don't death. The origin for this talk comes from two considerations. Recently, people are talking about what we call as second law violating microstates. For a very long time, it was the theoreticians who were talking about second law violation. And you know, when a theoretician says something, nobody believes it, except himself. Whereas when an experimentalist announces a result, everyone believes it, except himself. Okay? So it was in the realm of theoreticians. But recently they have carried out some experiments with single protein molecule dragged through a viscous fluid, and they have actually observed second law violating scenarios. In fact, for a very long time, it was the policy of physical review letter that if any paper contains the word second law violation, you don't need to send it to the referee, it can be rejected right away. They made an exception to that, and there was a paper that came in physical review letter about 11 years ago. The title of the paper was Observation of Second Law Violating Microstates. So I got interested as when the paper was published, and subsequently a lot of work has been done. And surprisingly, it is my thesis, that surprisingly I found that what these people are talking about as second law violation or second law violating scenarios is something which Maxwell about 140 years ago said in the context of demon. That's what I'm going to call it. The demon is, actually I should call it strictly Maxwell's demons don't die. Okay? So I have removed the word Maxwell to make that title very attractive. Okay. So my aim will be, if I'm able to show that the recent work that have come in the context of second law violating microstate, that it is actually equivalent to what Maxwell postulated in terms of a demon. What is the Maxwell's demon? Maxwell's demon is a creature which violates the second law. I can tell you that there are hundreds of ways of stating the second law. I will pick up a few of them. One of the standard statement of the second law of thermodynamics is that you cannot extract useful work from an equilibrium system. Or put it in another way, if you want to extract work from heat, you have to have two sources, one at a higher temperature, a sink at a lower temperature, and you should establish a flow of heat from higher temperature to lower temperature. And then if you are able to establish that gradient, then you will be able to extract work. If you have an equilibrium system, there are no temperature gradient, and hence you will not be able to extract work. If you are able to show through a Gadankan experiment, a thought experiment, because theoreticians are capable of only thought experiments, if you are able to show that the second law is violated, that will be a big thing. Then it gives a handle for the experimenters to how to translate that in terms of experiments. So what does the demand do? So I have imagine that I have a box full of gas at equilibrium. So the molecules, the gas is made up of molecules, and they are moving here and there. This is what I have a point.
Dr. Ready?
Oh, yeah.
That's the one.
Yeah, one.
I want that.
So I have a gas in equilibrium, and imagine that the lemon sets up a wall, and he has a door in the wall. What the demon does is, whenever a fast moving molecule tries to go from here to here, it opens the gate. In the same way, whenever a slow moving molecule tries to go from here to here, it opens the gate. The other way, it closes. When you see there is a molecule which is moving very slowly, if it tries to pass through that, the domain will not permit. Let us say the domain operates for quite a bit of time, then you will find that all the fast moving molecules have accumulated here, all the slow moving molecules are accumulated here. We know from Maxwell's distribution, the temperature is higher here, lower here. Once you have established the temperature gradient, I can run a Carnot's engine and then extract work from that. So the domain helps you extract work from an equilibrium system. Of course, for a very long time, people did not understand what exactly Maxwell meant by that. What Maxwell said was, imagine what the domain does. It tries to establish a...
I mean, when this happens, the fast-moving molecules are on one side and the slow-moving on the other side. Can we still call it an equilibrium system? I mean, is it still...
The whole idea is from the domain establishes a non-equilibrium, that is a temperature gradient in an equilibrium system. Once a temperature gradient is established, I can run a heat engine, extract work. Okay? Now, I'll come to that. I think you will find an answer in the sequence. Okay. So, what Maxwell exactly intended was that if you are going to have a statistical mechanical description of thermodynamics, what do we mean by that? For every thermodynamic quantity, for example, energy, a thermodynamic energy can be represented by symbol U. How do I calculate this thermodynamic energy from the point from statistical mechanics? So I define a random variable called energy. Let me define it by a symbol E. The thermodynamic energy is the average of the random variable energy averaged over a suitable ensemble. It can be a canonical ensemble if it's a closed system. It can be a microcanonical ensemble if it's an isolated system, or grand canonical ensemble if it is an open system. So there are two stages involved. I should define what is known as an energy, that's a fluctuating quantity in statistical mechanics. When I average that energy over a suitable ensemble, I get an energy, and I am going to relate it to the thermodynamic energy. Keep this in mind. So Maxwell said that if energy is going to be a fluctuating quantity, is it possible for me to visualize that what the demon manages to achieve, can it occur as a consequence of very natural equilibrium fluctuations that are ever present in the system? Is it possible that the system, when it fluctuates from one microstate to another microstate to another microstate, is it possible for you to observe the system in one of those very rare microstates which has this temperature gradient? Essentially what I am saying is, if you are going to assume that I am going to have all these molecules spread around uniformly, filling up the molecules going here and there, because no molecule is stationary, just colliding with each other and moving there. Is it possible in the process of movement, it is possible that for a short time all the molecules, fast moving molecules are here and slow moving molecules are here. After all, that is one of the possible microstates in the scenario. Statistical mechanics doesn't prevent you from the system from being in that state. So his idea was that
KPN, may I raise an objection here?
no, sure.
You are assuming that the Maxwell's demon is a large guy. In reality, he is a molecule.
I'm coming to that. I'm coming to that.
He is being bombarded
Yeah.
with molecules, so he's going to be disoriented in no time.
Yeah, sure. I'm going to come. In fact, Bernoulli gave this explanation and then said that he killed the Maxwell's demon. Okay? So there have been a large number of scientists who have made attempts to kill the Maxwell's demon. My thesis is physicists are not smart enough to kill the Maxwell's demon yet, and it lives on. Let me come to that. Okay. So this is what Maxwell's demon is. It is trying. Is it possible that the demon state, what I am going to call it as all the molecules here and all the fast-moving molecules on one side, slow-moving molecules on the other side, let me call it as a demon state. Is it possible for the demon state to come out of statistical fluctuation? Thermodynamics, it's not that, but in statistical mechanical description of thermodynamics, there is a possibility. That's what Maxwell pointed out. So let me start with this preliminary ideas. Let us start with that. Maxwell demon lives on. It was born in the year 1867. It's 144 years old now, but it is very much alive and kicking. At least twice it was pronounced dead. First time it was pronounced dead by saying that the Maxwell's demon, if it has to identify a molecule coming and going, the trapdoor has to be extremely small. It should be able to see the molecules. In that case, the Maxwell's demon has to be an extremely tiny creature of the molecular size. If it is extremely tiny creature of the molecular size, then the demon himself is subjected to the thermal fluctuations. And hence how we can operate the door. If obviously if you have a shaking hand and if your hand is all the time shaking, you can't open the door. This was the explanation that was given, but something very similar to what Professor Ramarao was saying. Bernoulli wrote a paper and then killed the demon, and subsequently Zurich information theoretic way, he killed the demon again. I am not going to go into the details because that will take too much away. Demon is very, there are two big volumes that have come about Maxwell's demon. In fact, it's a topic for a full semester course. So I am not going to the details of how it was pronounced dead twice. As I said, the demon proved to be too smart for the physicists. It has challenged the best of the minds. Presently, physicists have given. Also, it is the second law that is the most abstract of all the laws. It requires quite some thinking for you to comprehend the statements. In fact, I am going to make several statements of the second law. It is also the law that originated from a very, very mundane consideration. One of the most powerful laws, most exotic laws, most colorful laws in theoretical physics has come out of very, very mundane consideration about efficiency of heat engine. It started like this. Man has extracted work from animals, he had extracted from work from several mechanical devices. He then turned his attention to extract work from heat. When Joule, Thomson and Mayer showed that heat is equivalent to mechanical work, you have a big ocean at a given temperature. You should be able to. In fact, when Joule announced his result, there was headlines in the paper saying that energy problem of the world is solved. Because if you can extract work from heat, what is the difficulty? Then they slowly came to the understanding that it is easy to say that heat is equivalent to work. It's one thing to say that heat is equivalent to work. It's quite another thing to convert heat into work. If I give you a certain amount of heat and the entire energy is at a given temperature, you cannot do anything about it. The whole ocean you might have, it might be at whatever temperature it is, you cannot extract work from that. You need the source of heat at a higher temperature and the sink of heat at a lower temperature. This temperature gradient is very much essential, and this is essentially the statement of the second law, and discovered by an engineer, not a physicist, but an engineer, Sadika. So in the very, very early days, I am talking about the early 16th, 17th centuries, heat was considered to be a fluid. You can call it as phlogiston, or later it was called as caloric, with very unusual properties. It was a fluid. Since and temperature is something like a gradient. When water goes from a higher elevation to a lower elevation, heat is a fluid that flows from a higher temperature to a lower temperature. That's the analogy. Mayer, Rumford and Joule came and established unambiguously that heat is like work. A way of transferring energy from one system to another system. Like this confusion will always prevail because the caloric theory was in operation for about 300-400 years. Even though we talk about heat as something that is contained in the body, which is very, very wrong. I never say that. Suppose I tell you that so much of work is contained in this, it looks ridiculous question, right? But if I say that so much of heat is contained in this, it won't sound that ridiculous. But I can tell you both are equally ridiculous statement, because if it is equivalent to work, saying that so much work is contained in this body, if it is ridiculous, saying that so much heat is contained in this body is also ridiculous. But unfortunately, we have imagined heat as some fluid that resides in a body, and that mindset continues. So we have books on heat transfer, transport of heat from one body to another body, as if it is some quantity that I am transporting from one. What you are transporting is energy. There are two ways of transferring energy from one body to another body. One way of transferring energy is through heat. Another way of transferring energy is like works. For example, I throw it and it hits you, you feel the pain. That's how I am transporting them. Work. In the same way, heat is another way of transferring energy from one body to another. The moment it was established that heat is like work, then heat engines that convert heat into movement. Any movement is work. Movement came into existence. Then automatically the question arose: how efficiently can you extract work from heat? This led to thermodynamics. That's the starting point for thermodynamics, and the second one. Let me quickly go through it. I think all of you are very familiar with this formula. And Karna gave a very, very beautiful, simple derivation of this formula. But unfortunately, in our textbook, you will have that Carnot's engine, adiabatic process, isothermal process, adiabatic compression, isothermal compression, and things like that. Carnot did not have any use for these things. What he simply said was, if Carnot imagined that heat was a fluid flowing from higher temperature to lower temperature. When a certain amount of heat Q, of caloric heat, that's why I call it as caloric heat, falls from a temperature T1 to 0, the work done is equal to Q. That means you can completely convert heat into work. However, when it falls to a temperature T2, where T2 is less than T1, the sink is at lower temperature, but it is not at 0 degree Kelvin, 0 degree absolute temperature. then only a proportional fraction gets converted into work. That means T1 minus T2 divided by T1 minus 0 is this fraction of heat that gets converted into work. And he defined efficiency as W by Q, which is 1 minus T2 by T1. It's as simple as that. This is how he derived. In fact, you should, anyone who is interested in thermodynamics in a deep way, he should read the original work of Sadi Karman, where you will find that this is the kind of derivation that he does. So, he made the first statement about the second law of thermodynamics, saying that heat cannot be completely converted into work, while work can be completely converted into heat. Of course, it's very, very interesting how he came to that conclusion. His father was an engineer, and he was worried that the heat engines made in Britain were always more efficient than the heat engine that were made in France. He was worried about it. He was a Frenchman, he was worried about it. How come the French heat engines are less efficient than the British heat engines? He could not solve the problem, of course.
Excuse me, can I just ask you to clarify? So that work heat, that is possible 100% efficiency. You said it's possible that way.
Work to heat is 100% efficiency.
100%. Now,
Whereas
it's not like
heat to
close to 100%, but it is 100%.
You can. There is after all friction, no?
Yeah.
You can convert to
Yeah.
when the whole object comes to a halt by friction, the whole thing gets into heat, right? Yeah. Whereas it has come, that is, you have applied the brake on your car, it has come to a halt, heat is generated. You wait for that heat generated to rework and then push the car, it will never happen, right? And that's the statement of the second law. That's what Carnot said. He came to the conclusion, as I said, that for a very simple reason that, when a professor is not able to solve the problem, he hands it over to his student. Anyway, that I always do that. No prejudice with anybody. So when the father could not solve the problem, he called his son and said that this is the problem I have, it's your problem now you solve. And when the father explained to the son what is the problem, heat engines convert heat into work. The British heat engines which convert heat into work are more efficient than French heat engines. The first question that Sadi Karnot asked was, how come you are able to convert heat into work at all? In nature, you have the opposite process. The friction converts movement into heat. Tell me a natural process where is there anything called unfriction or anti-friction or no reversal, where spontaneously heat gets converted into movement and then pushes the car. So he says when it is not happening in nature, he was a very, very devout religious person. He said, he asked the question, when God is not able to devise any natural process where heat is spontaneously getting converted into work, how come man claims that he can do what even God is not able to do? He simply said that it's just not possible. If you try to convert heat into work, you will not be able to convert it with 100% efficiency. And then he derived this formula. And you can see even the best of the engines cannot have 100% efficiency in converting heat into. Of course, I leave it to your imagination why French heat engines are less efficient than the British heat engines. The simple fact is France is south of Britain and the time. See, at that time, in the initial day, they never realized the importance of the sink in the conversion of heat into work. The sink was the ambient temperature. The ambient temperature in France is higher than the ambient temperature in Britain, and that is the reason why it is not the French inefficiency that is responsible for their heat engines to be less efficient. It is simply ambient temperature. And that is probably the reason why in India we don't have very efficient conversion of heat into work, because the ambient temperature is very high. Like in winter, you will have the kind of temperature that you are finding now in Alabama, quite hot. Okay. So let us get back to that. Other statements of the second law, Kelvin and Planck's statement of the second law, no process is possible whose sole result is conversion of heat completely into work. Closure stated that no process is possible whose sole result is the transfer of heat from a colder to a hotter body. And his statements of the Carnot principle, no engine operating between two reservoirs, the source and the sink, can be more efficient than a Carnot engine operating between the same two reservoirs. Or all Carnot engines, sorry for the spelling mistake, all Carnot engine operating between the same two reservoirs are equally efficient. These are the various statements. Let me go a little bit deeper into these issues so that you will be able to appreciate when I connect the Maxwell's demand to the recent work. So consider a system that goes from thermodynamic state A to state B adiabatically. That means there is absolutely no transfer of energy in the form of heat between the system and the surroundings or between the system and the other systems. Then the work done, WA, this A stands for adiabatic. Adiabatic work done is independent of the path. Note, remember, work done being independent of the path is only true for adiabatic processes. In general, work is a path dependent. That means a small amount of work cannot be expressed as a perfect infinitesimal. This implies that in an adiabatic process, the work done during the process is independent of the thermodynamic path, implies the existence of a state function, let me call it as U, internal energy. It says UB minus UA du is equal to the adiabatic work done. Now I am going to inquire about the system going from A to B by a process which is not adiabatic. Am I communicating? Adiabatic process is something that happens in an isolated system. An isolated system doesn't exchange energy in the form of heat with the surroundings. So I am going to ask the question, if the system goes from state A to state B by a process which is not adiabatic, let us say the work done during that process, let me call it as WNA, not adiabatic. If this denotes the work, in general WNA is not equal to WA. The difference WA minus WNA is called heat. That is how we are going to define heat. Heat is a way of transferring energy. If there is a transfer of energy that has happened, you subtract from that transfer of energy the work done, that is energy change during an adiabatic process. So a non-adiabatic change in the work minus the adiabatic work is equal to, I am going to call that as heat. No caloric, no phlogiston. This is the definition of heat. A mechanical definition of what heat is. Like I am saying that work is not a property of the body. It is not something that is contained in a body. It cannot be expressed as a differential of a state function. So normally we represent W as minus PdV. Let us take a simple gas system, minus PdV. You can see that if I assume PV is equal to nRT, ideal gas law, you can show that W is equal to minus nRT dt plus nRT divided by T into dt. I can write it as some function of pressure and temperature into dt and some other function of pressure and temperature into dp. And if I differentiate this with respect to pressure and if I differentiate it with respect to temperature, they are not same. That is the statement that W cannot be expressed as a differential. You require a quantity called, integrating factor called. When W is divided by minus P, you get a differential, perfect differential, which we call it as dV. This is very, very clear. Now, yeah, this is what I said. You multiply all the terms by the integrating factor minus 1 over P, then you will find that the derivatives are same. That means you can, that minus 1 over P provide the integrating factor for work, and dV is equal to dB minus dA. So you can see dV is path independent. Whereas work is path dependent. A path dependent entity, if you divide by pressure, path dependent entity called work, if you divide by pressure, it becomes path independent. this is something very, very clear. Let us see whether heat is a path dependent quantity or path independent quantity. So let me symbolize heat by Q. Q is equal to du minus dV. W du is nothing but CVdT. This is effective heat capacity at constant volume plus PdV. And this assuming PV is equal to nRT, I can write it as CV plus nRT into dT minus nRT by T into dT. And I differentiate this with respect to pressure, differentiate this quantity with respect to temperature. I find that they are not equal. That means Q cannot be expressed as a perfect differential. What Clausius did was, if I divide heat by temperature, then this quantity is can be expressed as the differential of a state function. And that state function, he called it as entropy. This is the origin of entropy. You can see I am dividing Q by T. I'm going to call it by the new thermodynamic. He discovered a new thermodynamic variable called entropy in this process. So I am dividing the left hand side by T, right hand side by T. You can see if I take the derivative of this with respect to pressure, and if I take the derivative of this with respect to temperature, they are equal. So 1 by T provides the integrating factor for Q. And Q by T can be expressed as a perfect differential of a state function, which Clausius in the year 1842 named it as entropy. So when the system goes from a thermodynamic state A to thermodynamic state B, the change in entropy is nothing but the entropy at B minus entropy at A. I don't need to bother about what the path that it can take. In fact, the path can be even a non-quasi-static process. It can be an even irreversible process. What all I need to find out the change in entropy is, I have a quantity called entropy, which is a function of the thermodynamic state variable. If I know the entropy at B, if I know the entropy at A, the difference is equal to the heat. And the difference is what determines the change in entropy, and heat is T/Ts. Thus, entropy is energy divided by temperature. Okay. It took a very long time for us to identify correctly. Much later, the temperature is another way of measuring energy. So, change in entropy is energy divided by energy. It's a dimensionless quantity, and Boltzmann captured it in a very, very simple way and said that entropy is K log omega, where omega is the number of microstates. So entropy is a dimensionless quantity, but then thermodynamics, it has been defined as joules per Kelvin. So to make an equivalent between the statistical mechanical entropy, logarithm of number of microstates, the thermodynamic entropy, we introduced that Boltzmann factor, which takes the unit of joules per Kelvin. So entropy is a dimensionless entity. But historically, since it has come, this is the origin of entropy. It is joules per Kelvin. That means temperature is another way of another unit, another way of measuring energy. Okay. Having done this, Clausius said that I can whatever Carnot described, that heat cannot be completely converted into work. I can do it by a simple statement that the change in entropy is always greater than or equal to 0, and equality obtains when the process is quasi-static and reversible. So, in terms of entropy, Clausius stated the second law as ds is greater than or equal to 0. And of course, for a closed system, this is about for an isolated system. That is spontaneously, whenever a process happens, the entropy always increases. It can never decrease. That means, another popular way of saying it is that you always go from order to disorder, never the other way. So, a spontaneous process cannot lead to order from a disordered situation. Somehow I am not very comfortable with interpreting entropy as a measure of disorder. That is, how do you measure disorder? I just don't know. That is, if some person is mad, how mad he is, there is no measure. So I have my own reservations about calling entropy as a measure of disorder. But then anyway, that is how we are taught, What is entropy? You ask in interview any student, what is entropy? He will say entropy is a measure of disorder. So it is coming in this sense. Okay. Then for a closed system, Clausius stated the second law as ds is greater than Q by T. Essentially, it means that when you go from A to B, if you go in a quasi-static reversible way, what do I mean by quasi-static reversible way? You go from thermodynamic state to A to B, During the process, the system is remaining all the time in equilibrium. If you want the system to remain in equilibrium, that means the process has to be extremely slow. That's such a process, I am going to call it as quasi-static, almost static process. You find as if nothing is happening, but slowly something is happening, and it's an idealization. So ds will be equal to q by t. In any process which is not quasi-static, the change in entropy is always greater than what you calculate for a quasi-static process. For a quasi-static process, entropy is q by t. For an irreversible, quasi-static reversible, for an irreversible process, change in entropy is always greater than q by t. So this is the statement of the second law for a closed system. This is the statement of the second law for an isolated system. Okay. Let me not go. There is another delightful formulation of the second law, the Karathioderical principle. I'll just state that. Let us not go into the details, because usually this is not taught in the curriculum. It is about adiabatic inaccessibility. That is, in the neighborhood of any equilibrium state, there are states that cannot be reached from adiabatically. This is one statement of the second law, and you can show that this is equivalent to the statement of second law as ds is greater than 0. But I am not going into the details. But keep in mind that if you have an equilibrium system in a thermodynamic state, in the neighborhood of that there are states to which the system cannot go adiabatically. And it is the existence of inaccessibility, that is adiabatic inaccessibility, that is responsible for the existence of the state function called entropy, and ds is always greater than 0. So you are going to divide the space in terms of surfaces where from one surface to another surface there is a change in entropy. And you will always go from one surface to another surface of higher entropy. That is, mathematically this is what it means. I will not go into the details. So this is only to show that there is yet another abstract statement of the second law involving adiabatic inaccessibility. What we will require for our for the talk here, I will require second law in terms of free energy and work. So work is equal to, that is du is equal to W plus Q. That is the statement of the first law. Any change in the energy of the system comes from the energy given in terms of heat, coming in terms of energy given in terms of work. So Q plus W is equal to du. I am using the convention that work done on the system is positive, work done by the system is negative. If the process is isothermal, that is W is equal to du minus TdS. If it is isothermal, that means temperature doesn't change. I can write work as d of u minus Ts, because temperature is a constant. Then u minus Ts we identify immediately u minus Ts as a Legendre transform. Let me not go into the details and simply say that that is called the free energy. That is u minus T times S, u as a function of S and B, T as a function of u and B. And this is, sorry, yeah. So I have temperature which is defined as, this is the second law definition of temperature. Partial derivative of u with respect to S, keeping volume constant. The essential take-home point is that the change in the free energy in a closed system is equal to the work done. What is the relation between free energy and work in an irreversible process? Is there any relation that I can think in terms of free energy and work, and the work is an irreversible work? That is, the work done is in a process which is irreversible. I would like you to stop me at any time if I am saying something which you are not able to comprehend. Please stop me. My idea is that I would like to communicate some excitement I had in doing that work. I want to communicate a part of that excitement, if not the full excitement. So I would feel happy if you stop me in between if you have any questions. Okay? Okay. So I am going to probe the relation between free energy and irreversible work. So I am going to start with the closure statement of the second law. ds is greater than q by t. We have du is equal to q plus w, or w greater than du minus ts, because I am going to bring w here. This is equal to du minus q is equal to tds only for an reversible process. So W is greater than D of U minus Ts if the process is irreversible and isothermal. So W is greater than df. Thus, work done is greater than df in an irreversible process. In the reversible limit, I have work done is equal to df. So keep in mind that if I take the system from a thermodynamic state A to thermodynamic state B in an irreversible way, the work done is always greater than the change in the equilibrium free energy. Thus, we find that the second law of thermodynamics can be stated in several equivalent ways. Lest we forget, let me emphasize, the second law is an empirical law based on observation. That was what I was telling you. If you smell the second law, it will smell of human sweat because it is based on observation, experimental observation. Nobody has ever tried to prove the second law, even though Boltzmann made a very glorious attempt to derive the second law from Newton's law and he failed. And I don't think up till now anyone has succeeded in deriving the second law of thermodynamics starting from Newton's equations of motion. So nobody tried to prove the second law, nor did anybody think that it could be violated. Nobody thought even that it could be violated. So there is I have made an unproven, I have made a statement which I cannot prove, but you cannot find an experiment that violates the second law. Everyone believed that the second law operates, but did not know why the second law operates all the time. Then came Boltzmann, who made an entropy a statistical entity rather than a thermodynamic entity. So he was the first to introduce the notion of, statistics was a subject which the mathematicians were indulging in, and most of the time the mathematicians were advisors to kings who play gambling and they were trying to predict what are the chances that you will win and things like that. So physicists had never any use for statistics. In fact, there's a very popular statement, there are three kinds of statistics, and statistics. Okay? But it was Boltzmann who for the first time showed us that statistics can be used for making predictions about material properties. So he made the thermodynamic entropy as a statistical entity. Boltzmann had a hunch that the second law could be derived from the laws of Newton. Entropy should have a dynamical origin. It should have a Newtonian dynamical origin. He was of the opinion that macroscopic irreversibility can arise from reversible microscopic laws. That is, starting from Newton's equations of motion, he derived what is now known as Boltzmann transport equation for the phase space density of molecules in the dilute gas. Actually, I am not going to get into the details of Boltzmann transport equation, because that will take us far away from there. After he formulated the transport equation, then came the trouble. So there were two people, Schmidt's reversibility paradox. He says that an isolated system evolves from time t is equal to 0 to tau. If there is a spontaneous decrease in the increase in entropy, he defined actually a Boltzmann H function, which is minus of S. So let us formulate in terms of entropy. So essentially, Schmidt's objection to Boltzmann claim that he has derived the second law starting from the time reversal invariant Newton's equations was that if there is a spontaneous increase of entropy during this evolution, then the system, since the system obeys time reversal invariant Newtonian dynamics, it will end up at the same phase space point it started from. If I reverse all the momentum, it will end up at the same space point. That means during the reversal process, the entropy decreases, which violates the second law. Okay. But it's not very important. That it is only to say that there were objections to make Boltzmann's claim that the second law of thermodynamics can be derived from Newtonian equations. Of course, there is another paradox which is called Zermelo-Circum's paradox. I will completely avoid discussing about that. And come directly to the statistical entropy of Boltzmann, which is defined as minus kb summation over rho I log rho I where rho I is the probability. Now probability has entered into the physical description. Rho I is the probability that the macroscopic system is in one of its microstate indexed by I. I am going to sum it over all the microstates for a closed system, then I get the entropy, and KB is the Boltzmann constant. I put a negative sign because probabilities are less than 1. Log rho I will give you a negative, and I correct it with everything like this. So KB is now called the Boltzmann constant. If we assume all the microstates are equally probable, which is what one has a fancy name for it, ergodicity. If all the microstates are equally probable, then rho I is equal to 1 over number of microstates, which is identical for all microstates because all microstates are equally probable. Then we get the familiar expression, S is equal to KB logarithm of total number of microstates. Interestingly, this is the expression Boltzmann never derived. This was derived by Planck, but then he of course, it was obvious in the definition of H function, that is minus summation over rho I log rho I, it can be derived. It was Planck who derived this and but gave the credit to Boltzmann. It is engraved on his tongue. So Boltzmann entropy is consistent with the thermodynamic entropy of clouds as defined through the statement that the change in entropy is equal to heat divided by temperature. Thus, macroscopic behavior is probabilistic if we accept statistical mechanics. Despite the fact that we are not able to get statistical mechanics from Newtonian dynamics, let us keep that issue aside. We can take statistical mechanics as the starting point, and if we accept statistical mechanics, then the macroscopic behavior becomes probabilistic. The moment you invoke statistics for describing macroscopic behavior, you have to contend with inevitable and inherent statistical fluctuations. The moment you say the probability description, then you have to provide for behavior which are fluctuating away from the average behavior or expected behavior. Maxwell was the first to recognize that and state that the second law is of statistical origin, and hence there is a non-zero probability of it being contributed. To illustrate the limitations of the second law owing to its statistical origin, Maxwell proposed a demon which violates the second law, and that was the demon that I described at the beginning. The subtle idea is follows. Let us look at what the demon purports to do and ask if that would happen as a consequence of fluctuation inherent in an equilibrium system. You have an equilibrium system, but equilibrium system is not a dead system. Molecules are all the time moving. There are always ever present inherent equilibrium fluctuations. Is it possible for the system, an equilibrium system, is it possible for you to capture the equilibrium system in one of its second law violating microstates and then say that look, during this duration the second law is violated. So that is what essentially Maxwell had in mind when he proposed the demon. We should pay attention to the relation statistical mechanics has with the thermodynamics. So I have already told you, corresponding to every thermodynamic property, there exists a random variable in statistical mechanics. The average of the random variable over a suitable ensemble would equal the thermodynamic property. The average behavior is consistent. It is the average behavior that should be consistent with the second law. In this sense, the second law can never be violated. But I am going to look at the violation of the second law in the sense of Maxwell's demon. And I am going to show that the current developments exactly tally with that. A particular realization of the random variable need not be consistent with the second law. Maxwell meant second law violation in this sense and created a demon to pick up those microstates, those rare behavior of the macroscopic system. That behavior is not consistent with the second law. Let me say, consider a typical experiment of you have a cylindrical box full of gas. It's a thermodynamic system with a large number of molecules of the order of 10 power 25 molecules going here and there, and let us say it is in equilibrium. I am going to put exactly at the center, I am going to create a wall and ask the question, how many molecules are there on the left side of the box and how many molecules are there on the right side of the box. You will find invariably every time you do that experiment, you will find half the number of molecules on the left, half the number of molecules on the right. But for fluctuations, which are not even measurable, those fluctuations go like inverse of the square root of the system size. If n is of the order of 10 power 28, square root of 10 is of the order of 10 power 14, so you can see 0.5 into 10 power 24 plus or minus 10 power 14. This plus or minus doesn't make any difference to that. Suppose you extend this notion that every time I drop the middle ball, I will have equal number of molecules on the left and right side of the box. You start applying that law when the number of molecules becomes smaller and smaller and smaller. Instead of 10 power 28 molecules, imagine that you have, let us say, about 10 molecules. When you drop the partition at the middle, do you expect that every time you do the experiment, do you expect 5 molecules here, 5 molecules here? You will find there are situations where more than 5 molecules, maybe 7 molecules, 8 molecules on the left box and 2 molecules. So when the system size becomes smaller and smaller and smaller, there is a possibility for you to observe situations where you don't get equal number of molecules on the 2 partitions. This gives you a possibility if you are able to carry out. It's not connected. So if the system size that you are looking at, if the number of molecules that you are looking at are becoming smaller and smaller, you will find second law violating microstates occur often. But then even for a very small system, if you calculate the average behavior, it will be consistent with the second law. That is, even if, for example, imagine that I have 2 molecules only. When I drop a box, second law tells me that 1 molecule on left partition, 1 molecule on the right partition. There is a possibility that 2 molecules are here or 2 molecules are here. But look at the average number of molecules in the partition, it will always be unity. So if you calculate average over ensemble, the average behavior is always consistent with the second law of thermodynamics. It is the fluctuating behavior, sometimes you will find that it is not consistent. And that is the reason why it took so much of time for us to look at experiment and show that, look, these are the, that is nowadays we have what are known as laser tweezers, where you can manipulate a single molecule, drag around a single protein molecule, and you can carry out experiments at very, very, very small length scale, nano and sub-nano scales. When you carry out that experiment, you find that several times that your experimental results are not consistent with the second law, and that is so we are able to, experimentalists could come up with a definitive statement about second law violation in the recent times, because our tools to probe the system at very, very small length scales and time scales, we have very refined tools. So this is what I had explained. That is, if I have just 2 molecules, you can see that these are the 4 possibilities. Average behavior, average number of molecules on the left is 1, average number of molecules, so it is consistent with the second law. But you can see these are the 2 states which are violating the second law. You can observe these only when there are less number of molecules. This is a very pathetic case where I have just 2 molecules. I don't think experimenters have come to the statement that they can probe molecules at 1 and 2.
Does that mean that as the system size reduces, the probability of finding such states increase?
Yes, probability for finding such states increases. And that is how they found it in the experimental situation. Okay. So what are the recent developments? Sure, please.
You mentioned something a while ago that disturbed me very much. And I tend not to believe that. I respectfully say that. You said that Boltzmann's statistical, because his computation, it was done by Planck and not Boltzmann. In other words, that's
no. Boltzmann did the work.
Huh?
Boltzmann did the work.
Right.
But he gave his expression for entropy. In fact, he didn't even call it as entropy. He called it as H. Boltzmann H function, which is summation over rho A log rho I, or PA log PA. If you put a negative sign, H function becomes entropy. This is what Boltzmann did. But in his term, you will find that entropy is S is equal to K log omega. That expression was, you never find that expression in Boltzmann's papers. That expression was derived by Planck. But it is there in the Boltzmann's expression rho A log rho A. That's what I showed, no? If rho A, all rho A's are equal, so rho A is equal to 1 over omega, 1 over number of microstates, so S is equal to K log omega. I never said that Planck did Boltzmann's work. Boltzmann was the one who did Boltzmann's work. Planck derived S is equal to K log omega from Boltzmann's statement of H function, or with a negative sign, we can call it as entropy. Let me be very clear. So, credits have to be given to where it is due. So, Planck never tried to rob Boltzmann of the credit discovering entropy. In fact, that was the reason why he engraved it on Boltzmann's tomb. In fact, he was the person to call it as Boltzmann entropy. Boltzmann never used the word entropy, he called it as H function. It is called Boltzmann's H function. Fi log Fi or Pi log Pa. Summation over I with a negative sign is called H. Okay. Subsequently, Maxwell realized the importance of Boltzmann's work, Gibbs, Planck, and then subsequently Einstein. These were the people who formulated statistical mechanics. That is, if you want to identify who are the founding fathers of statistical mechanics, Boltzmann, Gibbs, Maxwell, and Einstein. These are the 4 people I would pick up as the ones who have given rise to the subject called statistical mechanics. Okay. So, in the recent times, we are talking about entropy fluctuation theorem, heat fluctuation theorem, and work fluctuation theorem. Of these, I will take up in detail the work fluctuation theorem, and I will show you that how the Maxwell's Riemann and the recent developments in fluctuation theorem are consistent with each other. So I told you that if you have a process that takes the system from the thermodynamic state A to state B in an irreversible way, then the work done in the irreversible process is greater than dF. I want to ask, what does it mean? How do I look at it statistical mechanically? Thermodynamically, there is no problem. There is only one. Definitely, there is no scope for probability in thermodynamics. There is no scope for fluctuations in thermodynamics. All the thermodynamic quantities are definite quantities. So W is greater than dF makes a lot of sense in thermodynamics. But when you translate the same statement, W is greater than dF, and when you want to look at it statistical mechanically, I want to know what is the meaning of this statement. Imagine that you have an experiment that represents the switching process. I am calling it a switching because this the irreversible process can be never represented as a path in the thermodynamic phase diagram. At best, you can say that when you go from A to B, the system is in A, disappears at A and appears at B. I cannot show how it has gone. If I have to show that how it has gone, then the process has to be necessarily quasi-static reversible. Irreversible processes cannot be represented by a path in a phase diagram. That's why I'm going to call it as switching process. Different switching experiments, all carried out with the same protocol, can in principle yield different values of W. Let me explain what do I mean by that. Imagine a situation where I have a cylinder fitted with a piston. I have a volume, the gas is occupying a volume V1, and I pull the piston and increase the volume from V1 to V2. This is the process that I am talking about. Essentially, I am going to make changes in the volume of the system. Now, I am going to ask the question that when I carry out this switching experiment from V1 to V2, if the change in volume happens over infinite time, that means if I pull the piston extremely slowly so that I take infinite time to change the volume of the gas from V1 to V2, then every time I do the experiment, I will get the same work. But I am going to imagine a situation where I just catch hold of the piston and move it over a finite amount of time. Now, when I do it again, I expect the work done to be different. Why it is going to be different? Because a simple way to imagine is that At the time I start that experiment, the system can be in any one of its statistical microstates. Depending upon which state it started with, the work done can be different. That is one way. Another, during the process, the system is always in contact with the heat bath. System exchanges energy with the heat bath. It gives energy to the heat bath or takes energy from the heat bath. This is happening all the time, randomly. A random process can never be reversed. If you do it very, very slowly, then at every stage the system is in equilibrium with the heat bath, and hence equilibrium work done is equal to change in the field. Okay. Now I am going to ask the question that if the time taken to carry out the switching experiment is finite and not infinity, then we have to deal with an ensemble of work values and not just one value. This statement W is greater than D, what is the meaning? When I have an ensemble of work values, let me collect all that ensemble and then represent it by a histogram, which I call it as probability density function. So I have a row of W which describes the work ensemble that I am talking about. So let the ensemble of values of W be denoted by omega. It is quite possible that several elements of omega will be less than delta F, violating the second law. This is the second law violation that I talked about. So let the probability distribution rho of W, I'm parameterizing it by a tau, where tau is the time it takes for you to carry out that experiment. In the limit tau tending to infinity, you will find that it reduces a delta function. That is the quasi-static limit, reversible limit of tau tending to infinity. We shall have rho of W as the rho of delta function of W minus. If tau is finite, then the probability of the second law violation is given by integral of this density function over minus infinity to plus infinity. That means I am going to look at the ensemble of experiment that I have done, and I am going to carefully note down the work that has been measured in each of these experiments. I am going to look at those work values which are less than the reversible work. And I am going to say that these are the scenarios in which second law is violated. One can see if tau is large but not infinity, then we can expect this ensemble rho of W to be a Gaussian, and you can have you can see for a Gaussian distribution it has only the first two cumulants. All higher order cumulants are there is cumulants are something like equivalent to central moment about the average value. Yeah.
Why is the integral starting from minus infinity? Should not be 0 to df or?
No, work done can be positive or negative depending upon whether the system is doing the work or you are doing work on the system. So in general, you cannot have anything less than minus infinity. That's the reason. In practice, it will be from some value, minus 10, minus 100, depending upon the kind of unit vector. So formally, the probability of second law violation is given by this. For obvious reasons, P is called the probability of violation of the second law. But as I told you, if I calculate the average work done by saying that the minus infinity to plus infinity W rho of W dW, that average work, average W, will always be greater than the reversible work. There is absolutely no question about it. Okay? This is essentially coming from the fact that your exponential function is a convex function. It is the convexity of the exponential function that is responsible for that. But we are not talking about second law violation in that sense. We are talking about second law violation in the sense of Maxwell's theorem, which says that there are scenarios, experimental scenarios, where you have W which are less than reversible work. That is the reason why I am integrating from minus infinity to WR or delta F, where delta F is the change in free energy between the two equilibrium states, that is the state before switching, the state after switching. Okay. Our interest is to find out how P changes when tau increases. Let us figure it out if we can do some analytical work on this issue. That's I am essentially coming to the work that I have done. Let me do it. I have about another 10 minutes.
Maybe 5 minutes.
Oh, sure. I will be able to do that. So when tau increases, the distribution shall become Gaussian with smaller and smaller variance. And let us substitute the Gaussian distribution in that integral and carry out this integral. This is very, very straightforward. if you do that, carry out the integral from minus infinity to WR minus average W divided by square root of 2 sigma tau, you will find that this is equal to half minus half of error function of this quantity. If you calculate it, you will find that actually this quantity increases and saturates upon half. For large tau, we have the Callan-Dalton theorem fluctuation dissipation theorem, which tells me that the average work minus the reversible work, which we call it as a dissipation in an irreversible process, which is equal to half beta sigma square, you will recover it from the general expression. And if you substitute, that is, if you are very close to process reversibility, I can substitute this expression in the error function. I will find that P of tau is half minus half of error function of this quantity. You can see in the limit of tau tending to infinity, this goes to 0. So the whole quantity goes to 0. I have P of tau in the limit of tau tending to infinity goes to half. This is a paradox here. It's a, of course, though this result seems counterintuitive on the face of it, if you define dissipation as a random variable, W average W, that is, the dissipation is defined as an average of the work done minus the reversible work. In the limit tau tending to infinity, dissipation goes to 0, as one would expect. The reason for the seemingly contradictory result, that is second law violating result, is due to the fact that when tau tends to infinity, both the dissipation and the variance of work, standard deviation goes to 0, but then sigma square is proportional to the dissipation, and hence sigma w is much, much larger. So you have a scenario where the Gaussian density collapses into a delta function in the limit of tau tending to 0. In the process of collapsing, the average Gaussian goes to 0 faster than sigma going to 0, and hence you find that the second law violation probability increases in saturated. But this is consistent with the prediction of Maxwell in terms of the. So the moral of the story is that the Maxwell's lemon cannot be won over, it cannot handle Maxwell's lemon, and anybody who is interested, they can look at our recent work on this and note on the fluctuations published in 2000. Thank you very much. And
questions? In Monte Carlo simulation, how would you try to sample those systems which are violating?
no, I will simulate the system and calculate the. I will do that experiment several number of times. Let us say about million times. I have million values of work, and then I'm going to take what is the reversible work, and I'm going to take all those values of work which is less than the reversible work. I'm going to take that fraction of that experiment. That is how many experiments have led to a value of W less than the reversible work, and that fraction is going to be the second law violation probability. I'm going to do it as a function of tau.
And then if you integrate it, it should saturate off at half.
And it does. I have not shown the results of the details of the results are in the paper, but that was not the purpose. The purpose was to show that the recent developments in terms of second law violation are not anything new, that it has been said 140 years ago by Maxwell. It's something like old wine in new bottle. That's what has been achieved. That's the take home point that I want.
And I'd like to make a critical comment, if you don't mind. What I feel is that in the materials or the regimes in which you are finding the second law violation are such low-dimensional systems. Thermodynamics fails, but Maxwell lemon becomes real. In other words, it's like smaller.
Actually, in fact, no one has observed a second law violation on a macroscopic system.
So, but
The experimental situation that I'm talking about are done on systems on a very, very small length scales and transient time. That is over a fraction of a microsecond you find that the second law is violated. So it is something like thermodynamics. I would not say that thermodynamics failed. Thermodynamics is a subject which is